Hi, and welcome to our presentation and demo about building internal development platforms leveraging the power of Kubernetes operators. My name is Dan Mckean, and I'm a product manager at MongoDB, and I'm joined by George Hantzaras, who's an engineering director also at MongoDB. We're responsible for enabling our customers and users to run MongoDB on or through Kubernetes.
Throughout this presentation, we're going to talk about the advancements in internal developer platforms, how Kubernetes has become the standard tool for the underlying infrastructure for building internal developer platforms, how Kubernetes can be extended, and finally, we're gonna see how by extending Kubernetes we can build platform capabilities, and a short demo how we build a database as a service.
So we're going to start by looking at internal development platforms and platform engineering. The term platform has been around for a while. Its most basic definition is a foundation that developers can use to build software applications. It provides a set of tools and services that make it easier to develop, deploy, and manage applications. But the term internal developer platform has sprung up as a new term in recent years to take things further. According to the CNCF, this should include reducing the cognitive load on developers and product teams by providing them with a set of tools and services that they can use to build, deploy, and manage applications. These are often described as golden paths. It aims to provide a consistent experience for developers, which can help to improve productivity and reduce errors. And lastly, it can be designed with the user in mind, and should be, which can make them more user-friendly and efficient. Platform engineering, unsurprisingly, is the effort that goes into designing, building, and iterating and maintaining such a platform.
So a platform offers and composes capabilities and services from many supporting infrastructure or capability providers. Platforms bridge the gap between underlying capability providers and platform users, such as application developers. And in the process, they implement and enforce desired practices that we call golden paths. Platform capabilities may comprise several features of an IDP, meaning aspects or attributes of a platform that users can use, such as observability tooling, managed databases, secrets management, and more. As platform interfaces, we describe the ways that platform capabilities are exposed to users of an IDP. These can include a CLI, a GitOps workflow using a tool like Argo CD or Flux, or developer portals like Backstage.
So now we're going to look at the rise of Kubernetes in platform engineering. While there's not that much data to categorically prove that the majority of IDPs are built on Kubernetes, it does seem to be the consensus in the industry that Kubernetes is winning as the platform of platforms. Reports from reputable industry analysts like Gartner, Forrester, or IDC often discuss the role of container orchestration and specifically Kubernetes in the IDP space. Many IDP vendors highlight their use or support of Kubernetes on their websites, and many publish case studies that mention Kubernetes usage within the IDP implementation. But why is Kubernetes making such a powerful impact for IDPs? Firstly, containerization. Kubernetes, unsurprisingly, excels at managing containerized applications. IDPs, by their nature, often involve integrating various services and tools, and Kubernetes makes this easier by packaging these components as containers, making them portable and easier to deploy and manage across different environments. IDPs can experience fluctuating workloads depending on their integration needs. Kubernetes facilitates automatic scaling of resources up and down based on demand, which ensures efficient resource usage and optimal performance. IDPs often orchestrate complex workflows involving multiple services. Kubernetes excels there, automating deployment, scaling, and networking of these services within the IDP. Kubernetes offers a platform-agnostic approach, allowing IDPs to run on various infrastructure platforms, cloud, on-premise, or hybrid, without needing to rewrite the code for each app environment. This gives flexibility. And declarative management. Kubernetes inherently uses a declarative approach where you specify the desired state of your application, and Kubernetes manages achieving and maintaining that state. This simplifies IDP management and reduces configuration errors. In essence, Kubernetes provides a robust container orchestration platform that simplifies IDP development, deployment, management, offering scalability, flexibility, and efficient resource usage. But Kubernetes hasn't always been ready to be the platform of platforms. There's been a few key developments. Originally, Kubernetes focused just on container orchestration, but huge improvements in extensibility have meant it can provide a platform for far more, like databases, security systems, and other cloud-native components. As well as extensibility, the CNCF has fostered an amazing, rich ecosystem of tools and services that can be deployed and managed on Kubernetes. And standardization and abstraction have played a big part. They've meant that Kubernetes has become far more interoperable, and the abstractions have provided simplified management. The aim is to make the underlying complexity invisible, further solidifying its role as a foundational platform. And lastly, there's various extensible interfaces which make integration with external tools much easier. Container Storage Interface provides a well-defined API for attaching, mounting, and managing persistent or ephemeral storage for containers. Container Runtime Interface acts as a bridge between Kubernetes and the underlying container runtime engine, like Docker or Containerd, in each node of your cluster. In simpler terms, it allows Kubernetes to talk to different runtime environments without needing to be rebuilt for each one. And Container Network Interface defines how network plugins manage the creation and configuration of network interfaces. This allows you to use various networking solutions with your clusters, providing flexibility in how containers communicate. However, nothing is perfect, and there are often discussions about how Kubernetes is potentially becoming too complex. While it can handle various deployments, it might not always be the most efficient choice. And the future may see a balance between leveraging Kubernetes' strengths as a platform and using simpler tools for specific needs. But abstraction might yet provide the solution to simplify Kubernetes.
Before we go further to understand how some of those key developments have happened in a more practical sense, it's critical to recap some of the fundamentals. So we can dive into the control plane, which acts as the brain of the operation. It manages the worker nodes and applications running on them. So there are multiple components on the control plane. The API server acts as a central point of contact. It receives requests from the users and applications to manage resources in the cluster. The scheduler decides where to run pods on the worker nodes. It considers factors like resource availability, pod requirements to ensure efficient allocation. Controller manager is a collection of controllers that together ensure that the state of the cluster matches the desired state. And we'll come back to that in a minute. And finally, etcd, which is a highly available key value store that acts as the cluster's single source of truth. It stores all the configuration data about the cluster and its resources. These components work together to automate and manage the lifecycle of containerized applications within the Kubernetes cluster. It's worth digging a little deeper into the controller manager and the control loop. They're intertwined concepts in Kubernetes, and they're also critical as we start to talk about operators. As mentioned, the controller manager is a collection of controllers that together ensure that the state of the cluster matches the desired state. It's made up of several controllers. Examples include the replication controller, which ensures a desired number of replicas are running for deployment. The endpoint controller, which maintains a list of pods that provide a particular service. Or the namespace controller that manages the creation and deletions of namespaces in a cluster. Now, each controller follows a control loop pattern. Initially, we have the getting the desired state. The controller retrieves the desired state for a specific resource, like number of replicas in the deployment, from the Kubernetes API server. Then you get the current state. So again, the controller queries the API server to determine the actual number of pods running. And then the controller compares the desired and current state. If there's discrepancy, it issues commands to the API server to take corrective actions like scaling pods up or down. Now, the control loop is the core principle behind each controller within the controller manager. It's a continuous iterative process that ensures the cluster state remains aligned with the desired state defined in Kubernetes configuration. Control loops enable self-healing. If a pod crashes, the control loop automatically detects it and launches a new one. Scalability. So when pod replicas need to be adjusted based on demand, the control loop ensures the automatic scaling up or scaling down. And consistency. So the control loop continuously works on rectifying any deviation from the desired state, keeping the cluster in a stable and predictable condition. So in essence, the controller manager acts as the conductor orchestrating the control loops of individual controllers. These loops constantly monitor and react to changes, ensuring the cluster maintains the desired state.
So now we're going to take a look at how Kubernetes can be extended. The inbuilt controllers of Kubernetes are critical, but one of the most significant developments made to Kubernetes in recent years is the ability to extend Kubernetes with custom controllers. What if you need to manage something beyond the basic functions? That's where these custom controllers come in. Custom controllers are user-defined programs that extend the capabilities of Kubernetes. They work in conjunction with custom resource definitions to manage custom resources specific to your needs. Here's a breakdown of how they work. In a custom resource definition, you define, using YAML, the schema for your custom resource. This essentially creates a new type of object that Kubernetes can recognize and manage. Custom controllers, typically written in Go, then interact with the Kubernetes API and follow the same control loop pattern as built-in controllers. They get the desired state, they get the current state, and then they reconcile, comparing the desired and current state. And if there's any differences, they take action to achieve the desired state. There are several key benefits of custom controllers. They extend the native Kubernetes functionality by enabling you to manage resources specific to your application or infrastructure needs. They allow you to manage these resources, these custom resources, in a declarative way. You just define the desired state of your custom resource, and the controller handles achieving and maintaining it. And automation. Custom controllers automate tasks related to managing your custom resources. For example, rolling updates to your pods.
So what exactly are Kubernetes operators? How do they fit in with custom controllers, and how are they different? So operators package up custom controllers and a few more components to make it easier to deploy and manage applications. So where a custom controller executes a single control loop to manage a specific Kubernetes custom resource, operators not only package multiple controllers, but also additional assets needed to deploy and manage an application. These can include CRD definitions specifying the custom resource type the operator manages, controller code, so the custom controller program that enforces the desired state for the custom resource, deployment manifests, which are YAML files defining how the application components like pod services are deployed in Kubernetes. Service manifests defining Kubernetes services needed by the application. Helm charts packaging configurations for the application in a standardized format. Documentation, monitoring tools like information and utilities for understanding and managing applications in Kubernetes. So by bundling these elements together, operators offer a self-contained unit for simplifying management within Kubernetes of an entire application throughout its life cycle. So why are operators so useful? Firstly, simplified application management by providing a single tool for deploying and managing applications throughout their whole life cycle. They offer a declarative approach where instead of writing complex deployment scripts, you simply find the desired state of the application using the operator's manifest files. Reduced errors by automating manual operational tasks, minimizing the risk of human error during deployment or configuration. Standardized packaging, operators promote a consistent way to package application. This standardization makes them more portable and reusable across different environments. Operators can be designed with domain-specific knowledge for particular types of applications like databases, messaging systems, and so on. And this expertise ensures the operator understands the application's intricacies and configures it optimally within the Kubernetes environments. Finally, a rich ecosystem of operators exists for various applications and functionality. So you can find pre-built operators for popular databases like MongoDB, monitoring tools, and other popular components, which saves you time and effort in managing them individually. But not all operators are alike. So Kubernetes operators can be broadly categorized into two types based on the resources they manage. Internal operators focus on managing resources that are entirely within the Kubernetes cluster itself. These resources are the core building blocks of applications deployed within Kubernetes. They use both in-build and custom resource types, including things like deployment, stateful sets, persistent volumes, and so on. On the other hand, external operators extend Kubernetes' reach by managing resources that reside outside of the Kubernetes cluster. This might be a self-hosted service running outside of Kubernetes, something running in one of the hyperscalers, or any other external service like MongoDB's Atlas Developer Data Platform. Despite their differences, both internal and external operators offer the advantages associated with operators in general. So simplified application management, declarative configuration, reduced errors, and standardized packaging. And by leveraging the appropriate operator type, you can effectively manage both internal and external resource dependencies, leading to a more robust and streamlined application deployment and management experience within Kubernetes.
So now we're going to move on to look at a demo. In the demo, we're going to focus on just one element of an IDP using Kubernetes and operators. To show that, we're going to demonstrate how you can build a database as a service into your IDP. We're going to use an external database as a service, MongoDB Atlas. Atlas is a software as a service offering value as a developer data platform of different complementary tools like search, analytics, and support for mobile apps, as well as support for serverless, time series data, geospatial data, and multi-cloud global distribution and resilience. We're also going to use the Atlas Kubernetes operator. It enables you to use the same tooling and processes to manage Atlas as you use for your services in Kubernetes. Atlas doesn't run in the Kubernetes cluster, but the operator allows you to use declarative configuration files that can be applied into Kubernetes, where the operator picks them up and using control loops makes changes to Atlas via the Atlas admin API. We're also going to build a GitOps interface for our users, using Argo CD as the mechanism to bridge the gap between the IAC files in the repositories and Kubernetes. This gives us a highly automated and standardized GitOps workflow, and in doing so cuts down on the expertise and permissions that individual teams need, as no more direct interactions with Kubernetes are needed. This provides a self-service mechanism.
Let's see now an operator in action and how managing external resources really works. An operator generally can be installed in a few different ways through kubectl, Helm charts, automation scripts. In this case, we'll use an automated way. So we consider having installed the Atlas CLI, and this makes installation and configuration super simple. So by running the Kubernetes operator install command, we firstly install the Kubernetes operator, but all the necessary setup happens in the background, such as creating new API keys for the operator to manage external resources. We can see that the operator is now running in our cluster. And if we go into our Atlas UI, we see that the relevant API keys have been created to use. And finally, in the background, the operator has safely stored the API keys as Kubernetes secrets, so we can use as we make the API calls to reconcile. So going to our text editor, we are going to create an Atlas project. This is defined as a YAML file. We apply in Kubernetes, and we see that the new custom resource has been created in Kubernetes. And under the hood, the operator has read the resource, and through the Atlas admin API has created this new project in our Atlas account. So we are now ready to deploy our first cluster. Back again to our text editor, simple YAML file to create an Atlas deployment. We describe the cloud provider, the instance type, the region we want this cluster to be deployed at. Again, a simple kubectl apply, and we see that the custom resource, again, is created in our Kubernetes cluster, and the operator has created it through the Atlas admin API in Atlas. So let's move on to build the platform interface as well. So integrating and exposing this database as a service functionality through a GitOps workflow using Argo CD. Now, again, installing Argo CD is pretty simple. Firstly, we'll be creating a namespace where all of the operator components are going to be running in. And then the installation of the operator is automated through an installation script. Just a single command, and a couple of seconds later, we can see all of the Argo CD operator pods are running in our Argo CD namespace. Now, next, we'll be creating an Argo CD application. We are going to define the repository that Argo CD will be watching to find new Kubernetes configuration files, and the destination Kubernetes cluster, the namespace that we're going to be using to deploy resources. Going into the Argo UI, we can see this TBAS application created, and we can monitor the sync status and so on. So to deploy an Atlas project through this interface, we use the exact same file as before, same configuration. The main difference is instead of kubectl apply, we just do a git push in our infrastructure as code repository. And then looking into the Argo UI, we see that our Argo application has picked up the change and has created the Atlas project custom resource in our Kubernetes cluster. And here it's same as before, the Atlas Kubernetes operator has picked up this custom resource and has deployed the new project in our Atlas account. Now deploying the cluster, again, we're going to use the same Atlas deployment file. We're going to be using it in the GitOps project that we just created, git push for the cluster creation, and all the same magic happens under the hood. Argo CD has picked up this change in, we can see this in the UI. It deploys this custom resource in Kubernetes, and then the operator creates the new database in our GitOps project. Now for the last part, as we've streamlined the deployment and management of new databases, we want to see how we can leverage the operators and make it easy to connect to those applications in a Kubernetes native way. So we'll be using a new custom resource called Atlas Database User in order to manage database access. And since each Atlas Database User is just another YAML file in our repository, the operator again makes that super easy to manage through our GitOps workflow. So we've already created a simple Kubernetes secret, which contains the user password. We have a custom resource definition for our database users where we refer to the password as we create the user. Similarly, as we did before, and through our GitOps workflow, Argo CD picks up the changes in our Git repository, sees the new resource here, and deploys the Atlas database user in Kubernetes. Now, an additional step here is that the operator creates a Kubernetes secret, which contains all the connection information we're going to be needing to connect to our database. If we explore the secret here, we can see the connection string that our applications need. So for the last part, we'll be creating a simple Kubernetes deployment. We'll be using the Mongo image to run a Mongo shell to connect to our Atlas database. And we read and use the connection string as an environment variable for our Mongo shell. We deploy this application. We use kubectl. And we can see that our Mongo shell pod is running. And if we inspect the logs of our pod, we can see that this pod has connected to our Atlas database using our connection string. Now, as this was the end of the demo, I'm pretty sure you were expecting fireworks towards the end. The good news is that when it comes to managing infrastructure in critical production environments, not having fireworks is a good thing. And if you also want to experience this transformation, this is a good time to prep your phone. In the next slide, Dan will show you a QR code where we can help enable you build an IDP through operators.
Through the link or the QR code, you can find a landing page that gives you all the information you need to replicate our demo, or to even take the next step and build your own IDP database as a service using MongoDB Atlas. Thank you very much for joining us.